I'll be right back. Once in a while, once in a while. I'm sure this video is gonna get demonetized, bro. I'm sure that this video gets freaking demonetized, but damn, is that a good song. Figure out how to end the simulation with an event. I'd like to do that today. For the ball model. Yeah, okay, so this is like termination conditioning or conditions or something like that. Coefficient of restitution for the collision, that we can do. So, okay, so I think, yeah, so there's that. Fix all of the, so, okay, so, fix model parameter values and initial conditions to be realistic with actual golf. Okay. Particularly club moment of inertia. Okay. This mimics. Okay. Okay, so this is going to be our biggest to-do object. Oops. Today. Is that really how that's displaying it? Oh, there you go. Okay. So so forcing functions, coefficient of restitution for the collision, add an effect on the first collision will reduce the velocity of the club by the correct amount. That should be okay, let's see, where are we at here? Oh, where did it error? Wait, what? Let's try this just to be like, see, the problem is that this triggers, let's see, I think, okay, if we need to just like go back and go to modeling toolkit. There's the language. Here's the events. The events is the most important thing. So in the continuous events section, where's the thing about chaining together multiple logical connectors? I think you just do an and, right? So I say, oops, I say and t is greater than 0. Let's see if this works. So then, yeah, so a lot of this work is just getting events right. Having a good event system is like a huge deal. Okay, so that doesn't work, but I think we might be able to do and. Is t defined? Okay, t is defined. Ugh, fuck. Wait, did it work or no? I don't think it worked. I think that that's old. Because it errored. So how do you use... But this is in the discrete events. But in continuous events... So basically this, just as a refresher, this one just tells the solver, do a root find and figure out when v is equal to 0, and then force a step at v equal to 0, which is chill. Bouncing ball. Okay, here. Okay, bouncing ball is chill. That one's easy because it's still just one root effect. I think. See, because the problem with this one is this happens when either of these are true, not when both of them are true. I mean, this syntax is just so kludged together. Is my feeling. I guess we need to make sure that we need to understand this one. But is there a way to use... So this is where I get... I guess we could just try it and see if it works. Okay, so I wanted to see if how it's passed. So okay, so this is what we do. So there's just this tuple convention. But the thing that I don't like is that even this does not let me define multiple conditions, because the thing that I need is I need to do the root find because I need to know exactly when it hits. I mean, we could just kludge it, but I'd prefer not to. So this is a preset time thing, but the thing about the discrete events is you have to remember it just checks the condition. Well, that's actually interesting. Oh, see, yeah, no, I forgot about that because then you have to manually add this t stop. But they have this special syntax, this, and then it just like does the t stops for you. But honestly, there's so much to keep track of that it's like. So I think maybe we want the imperative effects maybe. No, but see, it's still one condition. Hey, this is my. Let's see, how did I do it back then? Does this actually say? Let's see. You know what I could do? I could just I think we can just do this. Here, let's try this. So we're gonna put this into. All right, so wait, let's copy this whole example. So this is bouncing ball with a generic effect. So generic function effect or effect. Effect. Okay, so we have this. Let's just make sure that this runs. And cool. So now what we want to do is we want to check if integ.t greater than 0, then we are going to do this thing. So we need to figure out what the hell this means. U.v, like what is U? Is U the system, or is U? In some instances, a more flexible response to events is needed, which cannot be encapsulated by symbolic equations. For example, a component may implement complex behavior that is inconvenient or impossible to represent symbolically. MTK therefore supports regular Julia functions as effects. Instead of one or more equations, an effect is modeled as a tuple, where effect is a Julia function with the signature. Okay, so wait. Integrator UP context U, V, and PQ are the symbolic unknowns and parameters that are accessed by the function, respectively. Discretes are the parameters modified by effect, if any, and context is any context that is passed to. So what is the type of that? Oh, at least they have this. This line is important. Okay, so we should be able to do this. So if integrator, okay. So we're gonna be passing. So let's copy this. Go back to golf. We're gonna go up here and we're gonna define our. This is going to be the what are we trying to do? I don't even remember what we're trying to do. You know what okay, so here's what we're gonna try to do. We're gonna try to run it with a steady state effect. So let's get rid of this. Oh wait, actually, wait. Let's open this, undo the deletion, but then we're just going to close that. So we have this stop effect. If t is equal to 0, and we're already going to have, this is going to be the stop. But actually, are we allowed to set like, for instance, let's okay, before we do this, here's what we're going to do. I want to see if so I want to see if we can stop the ball when y equals 0. But I want to... I mean, I want that, but that doesn't work. But the problem is if we run this one just like this, then because oh, you know what we do? Okay, I know what to do actually. We make another one of these this thing, and we make it a parameter, right? Wait, we made it a parameter, right? I need to zoom out a little bit. Okay, so we make it a parameter. And we say this is going to be times has collided. And then this whole thing is going to be times has collided. Okay, and then this is going to be not this, but, or let's do this, has hit ground. So flag to indicate if the ball has hit the ground. Okay. But the problem is, we'd like to be able to do this. And this is just going to be has hit ground to true. And then we don't need to do this because those terms will just go to 0. So then here we're going to have this same thing right here. But the problem is, and I guarantee that, or I will say likely, this is going to, it's annoying that you can't affect the derivatives, honestly. Because if something is accelerating and then you stop it, I don't know how you... If you have ball sys. Yeah, I wonder, can you affect the derivatives? You should be able to affect the derivatives, right? Okay, so my guess is that this takes like 0 steps. Oh, no, it didn't. So that's nice. Okay, so now we need to go back to that plot. How did we do that plot where we want to plot this. Oh, Sol golf. This we're going to call Sol ball. Sol ball. So we're going to do Sol ball sys.y sys.has hit ground. Wait, did this fail or is that not true? Oh, this is going to be ball sys. Wait, I'm going to rename this. Sys ball. And this is going to be prob ball. See, okay, see, that's exactly what I thought would happen. So, okay, so now we're going to do this thing, but this is actually going to work. So we're going to have, but we need to make sure that we do this right. Or accessed, respectively discretes. So discretes is the 1, 2, 3, 4th thing. So in here, this needs to be. So wait, actually, within the context of this thing, but the thing is, this gets context, but where? Yeah, but I don't even understand, like, the function signature of this is when accessing variables of a subsystem, it can be useful to rename them. Okay, so this is like a dictionary-like object or some structure that allows you to access. Actually, that'd be interesting if we just did at show type of u. Um, t is less than or equal to 0. Else, here we're going to do, the thing is, where do I get the discretes? And then I want to do at show p. So we're not going to do anything. But basically, we're going to take this. I'm going to do this. I'm going to do this. And what is it that we're affecting? We're simply affecting a parameter. So that's going to be the discretes. That's going to be this. And it's going to be has hit ground. Now, v is not going to have anything. And this is going to be when y is 0. And we pass it as a continuous effect. So that should work. But we need to define stop effect. Once in a while. So this should, wait, what? Oh, has hit ground. Can we do not? We need to do not has hit ground. Because it, yeah. So actually, wait, we need to actually go back and try. So we need to try this one. I mean, honestly, it should just go straight to 0, right? It should be all zeros. Um, but okay, so now what we need is we need this plot. Because when does it think that it hit the ground? Um, what? How do we do it in this effect? To true. True. But then why didn't it go up? It should have gone up. Because in this one, let's just do this. I want to get to, where's the plot that I want? I want this plot. So this plot does what I expect, which is that when theta is equal to 0, do I need to do this? I don't think I need this, but we can try it. What if I just set it to 1? What happens if I set it to 1? They didn't change it, right? But I don't even know what I changed. But if I put true in here, hasn't hit ground. Whatever, let's just leave it as this for right now. And then let's remove the... It seems like that did work. But I just want to, like, play around with this, because this really is not behaving like it's supposed to. Like, in this plot, this thing needs to jump up. But it's not. I wonder if we just let's just turn off the effects and then see if it, for some reason. Mm. Eh. But that okay, but fine. But it does work, right? Which is weird. But let's just okay, so let's comment this out, and I'm gonna commit that we have. So let's turn this turn this to false, turn this to true. There doesn't seem to be a symbolic way to chain a symbolic continuous way to chain logical connectives for so then okay, but we can of course do this, and I'd like to do that maybe. What happened? Wait, did it this thing is really slow, unfortunately. I mean, it has to do a lot of stuff, but also it just feels kind of slow. Oh, see, wait, what happened? Oh, because oh, I'm just stupid. Okay, great. So this is the plot that we wanted. Now what we want to do is change this to steady state problem. Wait, really? Bro. Oh, yeah, no, that's fine. I'm chilling. I'm tripping, bro. Oh, seriously, man? Wait, I don't even understand why that would be the case. Okay, why is that? Why would that be? I don't even understand why that would be. Try to take one step and you'll see that the initial derivative is fine. Okay, alternatively, okay, so since this doesn't work, Okay, so what we're going to try now. So let's not do this. Okay, so continuous symbolic way to cause an effect. Continuous symbolic way to cause an effect when the ball hits the ground. Refactor we can delete, we can get rid of this, right? These are just going to be like, and this is just going to be like, or we can put this in test, that's fine. But place for me to copy and test stuff. And we'll just move, or maybe we don't even need to ignore it. Okay, whatever. So let's now we're gonna get rid of this. We're gonna get rid of this. We're gonna get rid of this, and we're gonna say this. It's not gonna do anything. But we want to look at P and we want to look at context. Name tuple has no field V. Where did that happen? BB effect? Oh. Wait, it's empty? Wait, what? See, that's... I swear this will error, but it doesn't make any sense. Wait, this isn't right. What? At show P. Oh, because it's calling the old one. Let's see what it says, because I don't even know what that means. Let's try it if we give it as a parameter. Oh wait, we need to yeah, but see, I don't like that it's all right. Well, let's just try to affect it, right? P dot has hit ground equals true. We can get rid of this too, or I'll leave it for right now. But I think I need to do. I think you no. I think you have to do dot p dot has hit. I think you need to do this. Wait. What is this third thing? Did I add that third thing? One, two, three. No, so they are doing it with three. But my problem with this setup is does it go into P? Like, so we do want to move this thing to this, right? That's for sure. The issue is that then it's not going to be in P, I think, but then how does it get referenced? Because we already checked that it's nothing, right? So this is going to error, key not found in P or whatever. Or yeah, exactly. But then where does it go? That's what I don't understand. But I can't change this signature. Or you know what? I think maybe I just Oh wait. If I provide it in both of them. Oh, hell yeah. Okay, we did it. How do you terminate an integrator? Did I not redefine this thing? I'm actually foolish. Okay, this is gonna work. There's no, yeah, I was like, yeah, you gotta, whenever you're doing stuff like this, you gotta be like, look, it's almost always user error. No method matching. Hmm. Oh, that's okay. Nice. All right, cool. So we have now successfully completed a to-do list item, which is so did our plot work? Our plot sort of worked. It didn't really move up like it was supposed to. I don't know why. Let's actually say for some reason the ball model has hit ground plot bug. The step isn't shown in the plot. I don't know why. Okay. What are we doing now? Okay. We have like 45 minutes left. A little bit less time than I was hoping, but I should have a couple hours later. We are so okay. So again, it's a bunch of technicalities. What I'm was hoping to do was um, actually start to uh, edit the first model and add in the force applied by your muscles. Um, because right now it's just like dropping the pendulum without any external force besides gravity applied to it, and that's kind of a that's not, that's not realistic. Um, so that's what I was hoping to do. But what I need to get done is just some learning about the framework of the modeling system itself. so yeah, so I wanted to do forcing functions. I wanted to do this. So these are the two things: coefficient of restitution and the forcing functions. Add an effect where we reduce the. So this would be cool. This would not be. Um. So this is sort of. So compose both models hierarchically. So this do after composing models. Because what we need to do is because right now what we do is we make the first model, we solve it, then we use some of the data from that one to solve the second one. But what we want to do is we just want to run both models at the same time. I mean, the thing is, it's actually a little bit less efficient to run both models at the same time because, like, I mean, for one case, if I didn't add, I guess one thing to note is like if I didn't add in the effect that stops the ball when it hits the ground, it would blow up and it would destroy my simulation anyways. So there's kind of a problem with composing models where like you do kind of want to throw out the first model because you don't want to just waste cycles spinning this club back and forth. That's kind of stupid. But I'll be right back. Okay. This is really weird. This thing where you send it to both of them is really weird, but it's okay. All right, so we are ready to. Wait, let's see. This we can do at the end at any time. For the ball model, we can't. The ball model, we can't pick a T-span. We need to run it until. Okay, so we can. So we did this. Oops. Steady state was tried, but failed with an instability ret code. I don't know why. Okay. But this seems to work pretty well. Okay. Oh shit! I never committed that. Oh wait, hold on. This one works. This set works. But cannot filter the can't handle the t greater than 0 requirement nor the ability to terminate the integrator. Okay, so refactor the README. Also got general function effect working. Okay, there we go. So now we can get rid of these because it seems like we have the best way to do it. I recall. Did you just create the human interaction with the golf? I remember. Yeah. So it's only pretty new to Video Studio. Didn't know. Oh, Visual Studio. Didn't know. Yeah, dude, you can do all sorts of stuff with the plots. Yeah. VS Code can do a whole bunch of stuff with plotting. I think you can even have interactive graphics in here. I'm pretty sure you can. I'm actually almost certain you can. At least I know for Julia, you can like, depending on which graphics backend you use, you can like do it. Okay, so now we deleted this. We got all this. So let me just read through here, see what we or actually I want to do like this for subs things. I want it to be a star. If I do this, what does it look like? All right, so let's do actually, I don't want to do coefficient of restitution. All right, so what we're gonna do is we're gonna try to compose them. I think composing is gonna be the coolest thing. Try to do it in 40 minutes. The forcing functions thing, I really want like 5 hours to just lock in and read a bunch of papers, like biomechanics papers to do this. So do they have like a good so we need to read a lot of this. Model validation will be important. Input output. I don't know what input. What is input output? Okay, here we. This is the thing that we need to read. Unfortunately, none of this is using the new language. I want to use the new language. So let's go down to. So we have this, then we have this. Oh, these are the connectors. Oh, I don't even know what that means, man. Okay, well we'll read the composing section because it should apply to the language. It's not like it's independent of it. It's just I wanted to see an example that's closer to the model that I have. Then validation will be useful because I returns true if and only if the units of equation are, so we'll definitely oh yeah, so okay, I definitely want to add so units validation. Because there should be a whole thing on, yeah, units. Okay, so let's just read the composition section. All right, so simple model composition example. The following is an example of building a model in a library with an optional forcing function. Ooh, okay, so that's like, oh, that's like exactly what we want. That's perfect. And allowing the user to specify the forcing later. Here, the library author defines a component called decay. The user then builds two decay components and connects them, saying the forcing term of decay 1 is a constant, while the forcing term of decay 2 is the value of the unknown variable x. Okay, so we have decay. So this just so you have an initial value. So this is just going to decay to 0 no matter what. But then you have a forcing f of t, and then you write compose decay 2 the f in the second decay is equal to the first x. And the change in the first forcing function is given by 0. So we're basically adding an equation into, well, it's into the composed model, but it's okay, so then this total set of differential equations becomes d decay 1. Ooh, actually, how did they LaTeXify this thing? I want to know how they did that. These are going to be like, so this is going to be like to do, done. Actually, let's do doubles because it doesn't need to be like this. This is going to be like tier 2 to dos. And this is going to be like, oh my God, stop, dude. This is going to be like, figure out LaTeXify the eeks or something like that. In general, well, whatever. I can write to-do list things all day. So the equations are that d f1 is equal to 0. And then this one, then the first x is equal to f minus a dk. Oh, a dk1 dot x. Oh, that's crazy. Okay. Because a is the parameter. And then the second one is decay2 dot f. But decay2 dot f, it doesn't say that this is, it doesn't say that decay. Okay, so I want to run this example. Okay, so let's just try to figure out decay2 x. look at these equations again. So decay2.x is the... Oh, it's going to be 2, right. It's going to be 2 because... But this one is just going to have f is 0. So this is just going to... So decay1.x is just normal exponential decay. But then this one has an initial change... Or it has a change of... But this is x. This becomes x in the model. So whatever x is, it gets... Okay. So it's going to be positive for... That's why it's positive for a bit. So that makes sense. Okay. The basics of model composition. It's warm out. Every abstract system has a system keyword argument for specifying subsystems. A model is the composition of itself and its subsystems. For example, if we have the equations of sys is the concatenation of get exist and equations of subsist. I don't know why this one's get ex and this one's equations. That doesn't... What is the difference between that? I have no idea. The unknowns, or the concatenation of their unknowns, etc. When the ODE problem or ODE function is generated from this system, it will build and compile the functions associated with this composition. Maybe we should try to build a simpler... Maybe we should try to build a simpler model. Isn't there like... I know that... I think Ayush... This guy Ayush... He's like the main contributor at this point. But he had a collide.jl. This is what I was looking for. A simple, performant, and accurate physics engine implemented in pure Julia. I mean, this thing is sweet. This thing is so sick. It really hasn't been updated. They collide from the inside. That's fine. Entities that touch exactly 2 circles at a distance equal to the sum of their radii are considered to intersect. To simulate things like Newton's cradle. Oh, dude, this guy is goated for sure, man. I never met him, but he's so sick. So wait, this depends on... Okay. But where's the model? This one probably doesn't depend on modeling toolkit. Okay. Is there docs? No, this is the whole thing. Okay. But I just want to know how he builds the model. The simulate. Simulate probably has... I think I saw like a sick animation. So world is... Where's world? D is differential export point. Oh, cool. Okay, yeah. Compose ODE system world. So this is empty except for whatever G is. What is G? G is gravity. Why is gravity two-dimensional? And then K is the spring constant. Okay. We want to figure out what are the eeks. Append eeks collect systems is in. Wow. This is like a dope example. VCAT collect values systems. So this is a dict, and this is a dictionary as well. Okay, so he takes the product of this and then he adds. Okay, so he make for oh wow. Okay, so for every pair of entities in his physics system, he builds a system for each pair. Okay, and then this is probably just the equations, the like just like we have the basic the momentum transfer stuff. This is probably the general. Wait, where was it? Okay, an entity, it has a shape, it has a position, a velocity, acceleration, and those are going to be a point, 0 point. But what I'm expecting is that in point, I think that's in up top. Point is just a static vector over some field. So this is a two-dimensional physics system, right? Oh. I'm pretty sure this is a two-dimensional physics system. Okay, so this is like, I want to try this because at some point I just want to see how it runs. This guy's so sick. Now he just develops modeling toolkit. What happened in May? Oh, wait, this is just him? I want to see all of it. I want to see all the commits. Till them merges. That's awesome. Okay. We can read about this all day, but that is super cool. That physics engine. That is really cool. I mean, it's using the full power of. That's what's so cool. But in any case, we wanted to read composition. Okay, I think I'm gonna end it here. Unfortunately, I'm gonna go for my run. So we didn't really get that far, but I did do a couple of things. But I do want to. I'll delete this one because I don't really need to do that. But I do want to try out the standard library. Actually, that's probably my most. All right, so this is just gonna be. All right, well, not the best, but I feel like I'm getting a grasp on at least the event system. I feel like I get for the most part. Now it's just a matter of making sure composition is really the next step. Then we'll do the forcing function tomorrow. Okay, I don't feel terrible about this. At least, some of the due diligence. All right.